Okay, let's see. I think we have everybody here that has to be here, 20 members and the candidate. So we'll get started. I'm told I'm the chair here, so maybe I need to say a couple of chairy things first. So Matt, this is Matt's defense of his master's thesis on the breakthrough Starshot project, where he's been looking at a couple of aspects of how to make the adaptive optics work by using sky-based beacons as the source of illumination for the wavefront sensing, and also how to what kind of limits need to be placed on the degree of correction in order to ensure passive stability of the nanocraft riding on this pencil beam, thrusting it at 10,000 G. And I won't steal his thunder by revealing the conclusion. We have some slides to go through for the public portion of the presentation. Then after that, we will go into closed session with the candidate and ask questions. I will say it has been a great pleasure to work with Matt for the last several years. This is the culmination of a very nice piece of work on the Starshot project. So I'm looking forward to this. I think I have my slides here, but if you can share your screen, Matt, so everybody can see them.
Yeah.
Go ahead.
All right.
Hello. Hello.
Hello. Okay. All right. Can everyone see my screen? Can you see my screen, at least Michael?
I can see your screen.
Okay, excellent. Let me set this over here and let me get started. Okay, thank you all for coming to my master's thesis defense. I'm super excited to share with you my work on the Breakthrough Starshot program that I've been working on over the course of my master's. The title of my talk is the Orbital and Flight Stability Models for the Breakthrough Starshot's AO system, which Michael gave you a little prelude to. So let me just jump right into it. So what is Breakthrough Starshot? So to answer that, I want to show you all this image. What you're seeing here is an artistic rendering of an Earth-sized habitable exoplanet. Although this image is not real, the planet and star that it depicts very much are. This planet is called Proxima Centauri b, and it was discovered about 4 years ago orbiting a star called Proxima Centauri. And what's really exciting about this planet is it's not on the other side of the galaxy. It's actually our closest celestial neighbor at a distance of only 4 light years. And although we know that this exoplanet is habitable, we don't know what the surface of it looks like. And that's what the Breakthrough Starshot Foundation aims to discover. So Breakthrough Starshot is an international engineering program aimed at designing interstellar space probes which can traverse the distance to Proxima Centauri within 1 human lifetime to take flyby photos of the surface of this other world. So to understand how to do that, how to do interstellar travel, let's talk about what makes interstellar travel so challenging. So 4 light years is our closest neighbor, but that's still a long distance. It's about 40 trillion kilometers. If you take the fastest man-made space probes sent by rockets, the Voyager 1 spacecraft, traveling at 17 kilometers per second, if it were pointed in the direction of Proxima Centauri, it would take about 70,000 years for the probe to reach our nearest celestial neighbor. So we need to, the Starshot system needs to think of a new way to accelerate spacecraft, both by reducing the mass of the spacecraft and increasing the acceleration possible. So first, we look at the Voyager spacecraft, which has cameras, magnetometers, power, telecommunications, all within a package of about 1,000 kilograms. Breakthrough Starshot aims to decrease the mass of this probe down to 0.5 gram. And within this package, it will have all of the same imaging, telecommunications, and power that the Voyager spacecraft has. And the Starshot system refers to this as the nanocraft. And instead of using rockets, which require a lot of fuel, and the bigger a rocket is, the heavier it is, and the more of that fuel goes to accelerating the spacecraft or the rocket instead of the spacecraft, Starshot aims to use the power of light. So a very large and very powerful laser projection system will exist on the surface of Earth, about 4 kilometers, and it will beam 100 gigawatts of laser power up to a extremely reflective and lightweight solar sail, about 4 meters in diameter, that the nanocraft will be attached to. And given these configurations, high power, low mass, the nanocraft can achieve 100 Gs of acceleration, and if applied over a time period of 10 minutes, can achieve 20% the speed of light, reducing that travel time to Proxima from 70,000 years to just about 20. So here's a little animation that the Starshot Foundation created. So you have the nanocraft attached to a solar sail, released in orbit from a mothercraft satellite. Down on Earth, you have a large laser projection array system, which will aim and focus its light through the atmosphere onto the solar sail. 100 gigawatts accelerates it for 10 minutes to 20% the speed of light, traveling the distance in 20 years. And upon arrival, will perform a flyby of Proxima Cen-B to take photos of its surface to send back to Earth. So this is what Starshot is. It's super exciting. And it's believed to be possible with the advancements of optics and laser technology to be possible within the next 60 years. And Breakthrough Starshot wants to determine what other aspects of the engineering are possible. And they've tasked us with analyzing the adaptive optics system for this laser. So the laser has to beam up from the ground through the atmosphere up onto the sail. Problem with this is Earth's atmosphere is turbulent. So when this beam travels through the atmosphere, it will defocus and it will deflect. And a lot of that laser light, if not all of it, will miss the sail entirely. So an adaptive optics system is required to fix that issue. And that's what I worked on and our group is working on. So let's just do a quick overview of what adaptive optics is. It's an example of a very simplified open loop AO system. So above the atmosphere, you have this is for a traditional AO system. You have unaberrated wavefronts which enter Earth's atmosphere and become distorted. So they go from being planar to distorted. Then a beam splitter takes these aberrated wavefronts and sends them off to a wavefront sensor. And the wavefront sensor measures the shape of these wavefronts and sends this shape to a deformable mirror. And this deformable mirror deforms opposite to that shape, such that when the distorted wavefronts reflect off of it, they reflect corrected. And the effect of this is an image which in telescopes is nice and crisp and high resolution. And without AO, the atmosphere would blur and reduce the image quality of an AO system, of the image. Starshot is kind of working in reverse, such that we start with a laser down on the ground that is perfect, and the deformable mirror has to pre-distort the wavefronts so that when they exit the atmosphere up here, they exit unaberrated and they come to a nice focus on the sail. So that's what the Starshot system is, but it operates essentially the same way. So for adaptive optics systems to work, for the wavefront sensing to work, they typically use what's called a laser guide star beacon. So for example, here's an image of one of the telescopes at the VLT with 4 sodium laser guide stars. It's essentially a powerful laser which beams up to the upper atmosphere, resonates with the sodium layer in the upper atmosphere, which sends a beacon back down through the atmosphere to the telescope. And that beacon light picks up the same distortions that the object of interest would pick up. And that beacon light then goes to the wavefront sensor and is used for AO. For Starshot, we have a powerful laser and we have it reflecting off of our solar sail. So easily enough, we can use the reflected light off of the solar sail as the laser guide star beacon for correction. Unfortunately, for the first 30 seconds, The atmosphere scatters light, scatters some of this outgoing light back, and the return light from the nanocraft can't be separated from the light that's scattered off of the atmosphere. However, this only happens for the first 30 seconds. At least the inability to separate these two happens for the first 30 seconds. And after 30 seconds, the nanocraft has accelerated fast enough that its velocity sufficiently Doppler shifts the light that comes back to Earth. So it redshifts the light that comes back. And so this redshift allows the AO system to separate the light coming from the beacon from the light that's being scattered off of the atmosphere. So this is the method for wavefront sensing that will be used for the majority of the launch period, from 30 seconds onwards. The problem is, what do we do about this first 30 seconds? And the proposed solution is, because the nanocraft is being released in orbit from a mothercraft, that we can attach a laser beacon to the mothercraft during that first 30 seconds. A beacon which is a different color and can be separated from the light being scattered off of the atmosphere. This mothercraft satellite would be referred to as the satellite laser guide star and would be the method for wavefront sensing for the first 30 seconds. So it's called the satellite laser guide star, an SLGS. However, there's a potential issue with an SLGS, which I'll illustrate in this diagram. At the moment of launch, t equals 0, the nanocraft is released in orbit at the highest point in orbit, called the apogee, from the mothercraft. Directly below it on the surface of Earth is the launch projector, which houses the 100 gigawatts of laser power, which will go up and accelerate the nanocraft. After a 30-second period of time, the launch projector will have moved in space because of the rotation of Earth. The mothercraft will have continued in its orbit, and the nanocraft will have begun to accelerate away towards Proxima. And in order for a laser guide star beacon to work, it needs to travel through the same path that the outgoing laser light will see, because it needs to sense the same distortion that the outgoing laser will see. However, we can see in this diagram that there's some angular separation between those paths, as well as a portion of path that is not seen by the laser guide star beacon. And these two errors contribute correction errors to the adaptive optics system. So the question then becomes, is there an orbit that exists which can reduce these errors for the first 30 seconds? So that's what I wanted to look at. I wanted to look at the viability of this method, the satellite laser guide star, for the use of by Starshot. And to do this, I had to create a fully parameterizable orbital model which could track the three-dimensional positions of the launch projector, the mothercraft, and the nanocraft in its orbit over this 30-second time, and see how the separations and distances of the beacon and the nanocraft change. And then after that, I wanted to look at how the residual errors affect flight stability. So AO systems remove the distortions. However, they never remove completely all of the distortions in the beam. So I wanted to see, how do these residual errors affect the flight stability? And so I had to create a model there as well as analyze the statistics of the residual errors in an adaptive optics system. And then we'll conclude with a discussion of all this work. So first, let's talk about my orbital model. So to minimize the error presented by a satellite laser guide star, there are two desirable orbital characteristics. One is highly eccentric, and two is having a large orbital size. And these two characteristics minimize the lateral motion of the satellite in the sky at the moment of launch. You can see that in this animation here, where the moment each of these reach their perigee, the highest point in orbit, the elliptical orbit moves much slower than the circular orbit. And you can see that right as they reach the peak right here, just how much slower a highly eccentric orbit departs in angle than a circular orbit. So there are 5 main parameters which describe how an orbit is oriented around a primary body, in this case Earth. And I created a model which allows you to input these 5 parameters, and then it uses Kepler's equations to determine the three-dimensional positions of the mothercraft over time. And so here's kind of an animation or a picture of what my model would output for a given orbit with an inclination and given eccentricity. So now that I have a way to model the positions of the mothercraft throughout the launch period, I needed to figure out how to model the positions of the nanocraft. And this needed to be done dynamically, step by step, because the position of the nanocraft at one moment depends on where it is the previous moment and where the launch projector is at that previous moment as well. So zooming in here, we can see a portion of the mothercraft's orbital trajectory. We can see 8 moments in time, where in blue, the mothercraft is continuing in its orbit. In green, the nanocraft is accelerating away from Earth. And then these 8 points in time where the launch projector is moving longitudinally around Earth. You can see at the beginning, they're on top of each other, and at the end, they separate both in angle and in delta Z. And this is the output of my dynamic numerical solution. So this model, which tracks and calculates the trajectory of the nanocraft, considers a couple things. The first thing is the time of flight of light. So light has a finite travel time. So if the nanocraft is at one point and the projector is at one point, the projector's aim has to lead the nanocraft in order for that pulse of light to impact the nanocraft one time of flight later. It also considers the power transfer loss of the energy from the launch projector to the nanocraft, and this considers the diffraction angle, the divergence angle of the beam, as well as the relativistic velocity of the nanocraft. The faster the nanocraft is, the lower force it feels from those photons. So now that I have a model which tracks the positions of the projector, the mothercraft, and the nanocraft for any given orbit, I wanted to analyze how these effects would arise for a given set of orbits. So what I have here are the range of orbits which I analyzed. So small orbits, which take a period of 1 day to orbit, or 10, which is a larger orbit. And then various eccentricities, orbital eccentricities ranging from circular orbits to very elliptical orbits. And then for each of those, I needed to understand how the errors arose in the AO system. So this angular separation in an AO system is called angular anisoplanetism. It's just a fancy term that's used to describe that angular error, and it's proportional to that angle. So the larger that angle, the bigger the error is in the AO system. And as a rule of thumb, this angle cannot exceed what's known as an isoplanatic angle, which is like the limit at which that angle can be. And for our system, it's 20 microradians, and it changes depending on the size of your telescope and the turbulence of the atmosphere. But for our system, it's 20 microradians. The other error associated with the difference in altitude between the beacon is called focal anisoplanetism. And in general, the error contribution is related to the height of this beacon. So the higher this beacon is, the lower the error contribution to the AO system can be expected. So now that I have an orbital model set up and how I can track the errors for each of those orbits, let's take a look at what the effects of different orbits are. So what I have here, plotted in 3 dimensions, is the final angular separation between the mothercraft and the nanocraft. On the X and Y axis, I have those different orbital parameters with small orbits to large and circular to elliptical. And vertically, we have the angular separation. What we can see from this plot is that small orbits that are very circular, the beacon separates really quickly and very far away from the nanocraft, almost 900 microradians in angle. This is much larger than that isoplanatic limit of 20 microradians. What we can see is for large orbits that are highly elliptical, there seems to be a region that might be within this 20 microradian limit. So what I did is I took this data and I plugged it into the equation, which allows you to determine the residual, the expected angular isoplanatic error that an AO system could expect with these angular separations. And that's what I plotted here. The color associated with this plot is the error associated with angular anisoplanetism, where blue is low error and yellow is high error, or an orbit which could be deemed unviable. In the x and y axis, we have the orbital parameters, where small orbits and large orbits, circular to elliptical. This thin strip up here arises from orbits that are highly elliptical and whose perigees dip below into the atmosphere. So these orbits are unviable, not because of angular anisoplanetism, but because the perigee, which is the lowest point in the orbit, dips into the Earth's atmosphere. So these orbits are not even possible. So we just throw them away. This other big region here is associated with those orbits where the beacon separates too far from the path that the launch projector laser light will have to travel. So again, these orbits are deemed unviable for that reason, and that happens for the same reason that we talked about in the previous slide, with small orbits that are circular. That leaves these list of potentially viable orbits. Potentially viable because it only considers angular anisoplanetism. So let's consider the other error, which is focal anisoplanetism. Here we can see a plot with the same axes, with blue being low error and yellow being high error or unviable. We can still see that strip of orbits which are unviable because of the perigee being too low. But this region down here, where the orbital period is low, meaning the orbit size is small, these contribute too much focal anisoplanetic error because the beacon is too low. So that's why this region is much smaller than the previous. This leaves, again, another region of potentially viable orbits, but only considering focal anisoplanetism. So to determine if there are any viable orbits for the satellite laser guide star, we need to consider the errors of both of these. And that's what I did in this plot. I took the errors associated with both angular focal anisoplanetism and I summed them together. And what you can see is those regions in this plot that are blue are considered to be viable orbits for the satellite laser guide star and could be used for the Starshot system for the first 30 seconds. So now that we've got a way to do wavefront sensing for the entire 10-minute launch. Yes.
So I have a question.
Sure.
So as you are defining those orbits, trade-off. So for instance, if you make this is really eccentric and goes far away, in that case, what is the trade-off? Because there must be something let you stop at some optimal point. Can you discuss about that?
Yeah, so the Starshot system, one thing I haven't quite said is that the Starshot system aims to not only send one spacecraft, but it plans to send hundreds of spacecraft, where each night at the same time, the projector, the mothercraft, and the where proximal will be are in the same line. And so each night, the projector can send another spacecraft. So having a large orbital period means you have to wait more days to send another spacecraft. So ideally, optimally, you would want an orbital period that is small so that you can send more of these spacecrafts more often. With regards to eccentricity, ideally you would want as high of an eccentricity as you can, but you want to balance that with having your orbit too close to the atmosphere when it comes to its perigee. So it would be a cost trade-off of whether or not you would want to spend more fuel to boost your orbit back up if you were to feel the drag force of the mothercraft entering a portion of the atmosphere when it gets closest to Earth. There also might be considerations on how tightly you can control an orbit over time, whether it'll decay or its eccentricity will change. I didn't analyze that, but that would be something that a future engineer could take this plot and perform that analysis.
Thank you.
Yes, you're welcome. Okay, so effects of residual error on flight stability. So now that we have a method for wavefront sensing over the course of the launch, we need to determine how tightly the correction needs to be performed for the flight to be stable. So let's talk about flight stability. So radiation pressure is what makes this whole thing work. It's the force of light. And what happens here, this diagram on the left, when a photon hits a perfect reflector with an angle of incidence, it reflects with an angle of reflection equal to its angle of incidence, meaning its momentum change is perpendicular to the surface at that point. Its momentum changes perpendicular to its force, to the normal of the surface. And because of the conservation of momentum, the perfect reflector has to feel a force normal to its surface. So when light reflects off of a surface, that surface feels a force normal to the surface, and the magnitude of that force is proportional to the angle of incidence of that light. This is for one photon on one spot on one flat, perfectly reflective surface. If you have a distribution of rays across the surface, the total force on that surface is the sum of the force distribution, and the force distribution is the result of the reflection distribution, which comes from each of those individual rays. So essentially, we're integrating this equation down on the bottom left across the surface. And what I have here is a configuration with a flat top irradiance profile and a flat sail. And with the sail perfectly perpendicular to the optical axis with no perturbances, the light accelerates the spacecraft along the optical axis. However, if there's a perturbance which causes this flat sail to deflect an angle, the angle of incidence of this light causes the momentum change, again, to be normal to the surface. And this sum of the forces is now pointing away from the optical axis, which causes the sail to move away from the optical axis and fall out of the beam and is no longer being accelerated towards Proxima. This is an example of a configuration which is unstable. This is unstable in the same way that balancing a pencil on its tip is unstable. So there needs to be a way to passively stabilize the sail throughout the flight. And here's the proposed design for that. And the idea for this is to have a spherical sail, spherical perfectly reflecting sail, and instead of a flat top or a Gaussian donut or a focus shape, we're going to use a donut PSF. You can see here that when the sail is perfectly in the center, the sum of the reflection distributions and the force distributions cause the force to be along the optical axis. Now, if a perturbance comes around, causing the sail to move over to one side, the geometry of the sail and the geometry of the donut sum in such a way that the sum of the forces push the sail back towards the center of the beam. So this essentially is the sail is trapped within a potential well. It's passively stabilized within the potential well of a donut, a PSF. And this works as long as the energy from a perturbance does not exceed the escape energy of this potential well. If that happens, then the sail exceeds one of the lobes of this donut and falls out of the beam and is lost. So what is a source of perturbance? So how does the sail even get perturbed anyways? So here we have a moment in time where the sail is perfectly in the center and the donut PSF is perfectly in the center of the optical axis. Now, residual tip tilt error would cause the donut PSF to decenter from the optical axis. So that's shown here, where any amount of residual tip tilt causes the focus to deviate from the optical axis. This deviation causes a force on the sail, which perturbs it off to one side. That's the source of perturbance. There's also residual higher order aberrations, which might result in a non-radially symmetric donut PSF that also can introduce lateral forces on the sail. But I'm only looking at tip and tilt, whereas higher order aberrations are being looked at by Ryan Luter in our group. So this talk is only going to be talking about residual tip tilt error in the beam and the perturbance forces that it causes. So this perturbing force from the sail decentering, from the donut decentering, sets the sail into an oscillation within the potential well. This oscillation is undamped because there's no atmosphere, so there's no drag force in which to dampen this lateral oscillation energy. And so the amplitude of this oscillation is determined by the energy of that perturbing force. Some moment later, an additional perturbing force may occur to this sail, which could increase this lateral oscillating energy. It's also possible that a future perturbance decreases this lateral oscillating energy. So what this means is the lateral oscillation of energy of the sail within the donut is the sum of all of these perturbing forces that have occurred throughout the course of the launch. And as long as the sum of these perturbance forces remains below the escape energy of the well, then we should be good. The question then becomes, what's the distribution of these perturbing forces? Are they large, and how frequently do they occur? Because those two factors determine whether this lateral oscillation energy will exceed the well energy of the donut. So that's what I wanted to look at next with statistics. And then how can you use these statistics to model the likelihood of success, which can determine the residual correction error needed for the Starshot system. So now let's talk some math and statistics. So by this thing in statistics called the central limit theorem, the distribution of these perturbing energies follows a normal distribution. That's shown here on the right. So the probability of a given perturbance is given by this curve, normal distribution. If the lateral oscillation energy at any given moment is equal to its oscillation energy the moment prior plus some perturbance, and those perturbances follow a normal distribution, then the probability that the sail's lateral oscillation energy increases is the same as the probability that the lateral oscillation energy decreases. So it's likely that the oscillation will be larger or it'll be smaller. It's equal probability. And in statistics, when this happens, this is what's called a Wiener process, which is heavily studied in statistics, and it's more commonly known as one-dimensional Brownian motion. So to demonstrate that, I created a quick little simulation here where I took the energy at one moment and I added a perturbance to it to determine the next moment's energy, and that perturbance was selected from a normal distribution with a mean of 0 and a standard deviation of 1. And in this animation here, you can see that random walk, that one-dimensional Brownian motion of the accumulated lateral oscillation energy of the sail, given a normal distributed perturbing energy forces. So for this particular simulation, the maximum achieved lateral oscillation energy was about 15 units. However, this is only for one simulation. This is not representative of what would happen every time. So I show that here on the right, where these sail energies, I ran 5 iterations of this simulation. And you can see here, this yellow simulation reached a max energy of about 20, whereas this orange reached a max of, say, only about 7 or 8. If I run this instead of 5 times, 500 times, we can start to see where this distribution starts to lie. We can see that given this setup, that the sail's energy never really exceeds 30 or say 25. Most of them are lower than that, with some extraneous ones, 1 in 500 chance of reaching maybe 40. So the question then becomes, what is the distribution of this, of the maximum achieved lateral energy given a certain amount of perturbing forces? And that distribution is called an inverse Gaussian probability distribution function, and it's depicted here. And this distribution is pulled directly from the simulations on the left here. And we can see that most of the time, given this simulation, the maximum achieved accumulated energy is somewhere between 20 and 7. It's very unlikely that a given maximum achieved energy will exceed 35. This would be analogous to flipping heads one after the other 1,000 times without flipping heads, without flipping tails. We can also see that it's quite unlikely that the maximum achieved energy is low. And this would be kind of analogous to flipping heads, then tails, then heads, then tails 1,000 times without flipping heads or tails twice consecutively. That's also kind of statistically low. And this behavior, which is a Wiener process, is what describes this shape. So now that we have the probability density function for the maximum achieved lateral energy given a distribution of perturbing forces, we can analyze the probability of launch success, the probability of flight stability by analyzing this PDF's cumulative distribution function. So cumulative distribution function describes the probability that the PDF is less than or equal to a certain value. So let me show you what that means. Say, for example, 20 was the escape energy of the sail. If you look at the value of the CDF here, 83% of sails have an energy equal to or less than 20 joules. Shown on the PDF, you can integrate from minus infinity to 20 to see the volume of the PDF, and that makes up 83% of the simulations. So this could also be worded as 27% of sails will have an energy that exceeds 20 joules. So if this were if 20 was the escape energy of the whale, then we could say confidently that 83% of flights of the launches will be successful. So now that we understand how to determine the probability of success given the distribution of perturbing forces, let's see if we can model that. And so to determine this probability of success, the shape of the CDF, we need to determine the factors that determine the shape of the maximum achieved lateral oscillation energy probability density function. And that's determined by how large individual perturbances are and how frequently they occur. Small perturbances, which happen not very often, can expect to have quite stable flight. But large perturbances, which happen often, we can expect the sail to probably fall out pretty quickly. So I wanted to create a dynamic model which allowed me to determine those factors. So I created a model which allowed me to track the axial position of the sail as well as the axial decenter of the donut PSF. And in this simulation, I assumed that the sail radius and the donut radius were equal, and they were their radii were about 2 meters in diameter. The decenter of the sail could be determined by, again, a normal distribution. And in this simulation, I could control what the distribution of these decenter values were. And then these were applied at a frequency called the Tyler frequency. And the Tyler frequency is an atmospheric parameter which describes how often the atmosphere's tip and tilt errors change. So over here on the right, I have pictured one particular simulation for the lateral position of the sail over a 30-second period, given a decenter magnitude of about 15 millimeters. And it looks like this weird fractal pattern, and that's because the oscillation frequency of the sail and the donut is about 30 hertz. So let me zoom in to 1 second in time, and you can see that oscillation frequency. How quickly the sail moves back and forth as a function of time. And the peaks of these oscillations are moving randomly, one-dimensional Brownian motion, with the introduction of these perturbing forces. So now that I've got the statistics set up and I've got a way to model the real life thing, let's see what the results are. So first I need to determine what is the escape energy of the potential well. So the way I did this is I took the sail, I set it off in one position within the donut, and I let it oscillate through one period, and I tracked the maximum kinetic energy of the sail within one oscillation, and that could be attributed to the potential well energy at that point. Doing this, I found that at the edge of the sail, or at the edge of the donut, the escape energy was about 68 joules. So The sail's lateral oscillation energy cannot exceed 68 joules. So taking that single simulation for standard deviation of 15 millimeters over the course of 30 seconds, I could determine this energy. And again, it looks like a fractal because of the oscillation periods being so quick that the lines squish together over the course of 30 seconds. But I can clean this up by tracking just the peaks. And the peaks of this describe essentially the oscillation magnitude of the sail within the donut. And you can see it follows that Brownian walk that we had predicted. So in an ideal scenario, what I would want to do is I would want to simulate this not for 30 seconds, but for 600 seconds, the whole 10-minute period. And I would want to do that not just once, but 1,000 times so that I could generate that probability density function to then analyze the CDF to determine the probability of success for, in this case, 15 millimeters of decenter. And I'd want to do that, say 5 or 10 times for different values of sigma to determine what the tolerance of tip and tilt is for flight stability. Fortunately, the simulation time for 10 minutes, so this was 30 seconds, but to do it for 10 minutes takes me 140 minutes to simulate. If I do that 1,000 times and I do that for 10 different sigma values, that's a little bit longer than the length of my master's degree. So I had to come up with a workaround, a different method to determine what this CDF would be for 600 seconds. And the trick that I found was it's easy to simulate shorter timescales. So say delta T's of under 3 seconds. I can do those quickly. I can run 1,000 of those for each of those time steps. And if I can understand how the probability distribution function changes for those small time steps, I can extrapolate that into the future to 600 seconds. So what I wanted to do specifically was do it for these time steps, determine the 90th percentile, essentially 90th percentile being 90% of flights are successful and it's stable. And then if I can understand that relationship, I can extrapolate it out to 600 seconds. So let's start with that. This is an example of 20 simulations for sigma 15 for a very small time period. Each of these simulations took maybe 7 seconds to run. So to run 1,000 of them was much smaller than an hour and 40 minutes. So the probability distribution function, which resulted from 1,000 simulations of 15 millimeter decenter, simulated over a course of 0.25 seconds, quarter of a second. The 90th percentile, the CDF at 90% was about 2 joules. So what that means is, given a decenter of 15 millimeters of the beam presented at the Tyler frequency, it can be expected that 90% of the time, the sail's lateral oscillation will be below 2 joules after a quarter of a second. I performed the same analysis for, say, half a second. So I doubled the time. And what I found was this 90th percentile doubled to 4 joules. So 90% of launches are equal to or below 4 joules in energy after half a second. I continued this for delta T of 1 second and 2 seconds. And what I found was every time I doubled the simulated time, the 90th percentile also doubled. Now, this was alarming to me because when I extrapolated this into the future, I found that it only took 8.5 seconds for the 90th percentile to reach the escape velocity, the escape energy of the potential well. So what this means is after 8.5 seconds, 10% of launches will have energies larger than the escape energy. And we're trying to do this for 600 seconds. So I looked back at the decenter value, which I had used to run these values, which was about 15 millimeters. And when taking that amount of decenter, given that the projector is 4 kilometers and the longest distance the nanocraft will be is about the distance of Jupiter, the OPD, the optical path difference error across 4 kilometers, at the end of launch can't exceed about 3 nanometers, which at 1064 nanometer wavelength light is about 0.003 waves of error, of residual error that is intolerable after 8.5 seconds, which is really bad, because this 3 nanometers of residual OPD far exceeds what AO systems are expected to be able to perform at in the timeline, the lifespan of the Starshot project. So the conclusion here is that stable flight may not be possible without a method to dampen these lateral oscillations. I said earlier that there's no drag force, so engineers on this program are going to have to figure out a way to dampen these lateral oscillations for this flight to be stable.
So Matt?
Yes.
I have a question.
Sure.
So this spherical sail has great advantage of passive auto aiming, but as you said, it's a very challenging. Anyway, one may need some active steering or control. So can you state some active steering consideration in this context? You may actively control the aiming.
Yeah, so the problem there is all of this was talked, as you had just mentioned, it's a passive method, right? There's no computer system which is tracking where it is and is correcting or adjusting. There's 2 issues. The first is the projector itself it's physically impossible for it to have some sort of active correcting system. And that's because of the travel time of light from the projector to the nanocraft over the course of the flight is too long. So for example, at the very beginning of launch, it takes about a second for a pulse of light to go from the projector to the nanocraft. If, say, halfway through the flight, it takes 20 seconds for the pulse of light to travel from the projector to the nanocraft. If the nanocraft begins to walk away from the center, it'll be 30 seconds before the projector knows that that's begun to happen. And by the time it knows, the nanocraft has fallen out of the beam. So because of the finite speed of light, it's physically impossible for this projector to have any form of active stability control, aim correction for the beam. Now on the spacecraft, because the spacecraft has to weigh 1 gram, it's difficult to, impossible at this point, and what we expect to have what modern spacecraft use, which are reaction control thrusters, which have these little tanks of fuel which can spit out at different angles and forces, which can actively control their position and attitude in space. The nanocraft has to be incredibly lightweight, so it's not going to have enough room aboard, mass-wise, to carry any fuel like that. So if there is to be some sort of active control on the spacecraft, it's going to have to be some new technology that we don't know about yet.
Thank you.
You're welcome. So just to discuss everything that I talked about through this presentation, Breakthrough Starshot is an initiative to make interstellar travel with a big laser. And in order for a big laser to work, you're going to need adaptive optics, and you're going to need a way to wavefront sense the distortion of the atmosphere. And the proposed solution was to use the mothercraft as a satellite laser guide star, and I wanted to determine whether or not that was viable. So to do that, I had to create a fully parameterizable orbital model, which allowed me to track these positions and the errors for different orbits. And what I found is that SLGS is a viable method for wavefront sensing over the first 30 seconds. And all you have to do is select one of those orbits and do a cost optimization on it. Now with residual error on the flight, I wanted to determine if flight was possible, stable flight was possible given residual errors. And more specifically, how tolerant the sail is to residual tip tilt errors. And I studied the statistics of these perturbing forces and created a model. And what I found was that the sails are not very tolerant to tip tilt at all, and that some sort of oscillation energy dampening is going to be required for the Starshot system. So that is that is the culmination of my master's report and presentation. I want to thank you all so much for coming to my presentation. And if you have any questions, I'd love to answer them now. And please feel free to unmute yourselves to clap or whatever, because. Yes, thank you.
Great job, Matt.
Thank you.
A quick question I have is, what effects do you think a very powerful laser might have on thermally exciting the atmosphere?
Yeah, that's a great question. So so 1064 is not thermal, it's infrared, so you can't see the beam, but it is a wavelength which through the atmosphere is highly transparent. So it's expected that its interaction with the atmosphere is going to be very low, especially with, it's 100 gigawatts, which is a lot of power, but it's spread out over an area of 4 kilometers. So the energy density at any given point in the beam from the launch projector up through the atmosphere shouldn't hopefully be too large to cause aberration distortions that couldn't be sensed by the wavefront sensor. I haven't done the analysis on this, but that's my answer to your question.
Thank you.
Yes.
Do you expect that that could change with global climate change?
Hopefully not. I do not. At least not where the projector is expected to be, which is in the Atacama Desert in Chile. The atmosphere is very calm, and atmospheric seeing and light pollution is, seeing is good, pollution is low. So, so yeah, no.
Thank you.
Yes.
Matt, that great presentation. Thanks for sharing it with us.
Thank you, Ben.
I think the thing that seems interesting to me about this project is it seems like you must have some really complex time requirements, both from the orbital separation from the mother satellite that you were talking about, and from the AO response rate as the nano satellite gets further and further away. Do you have any thoughts about how fast your AO system is going to have to be with all of these complex time variables coming into play?
Specifically, no, but in general, yes. The frequency at which the atmosphere changes is known as the Greenwood frequency, and it depends highly on where you are on the Earth and how turbulent the air is above your given site of observation. But at 1064, the frequency at which the atmosphere changes, actually rather, I know the time period, which is about 5 milliseconds. So every 5 milliseconds, the atmosphere changes. And so the adaptive optics system needs to have measured the distortion of the wavefront and corrected it every 5 milliseconds, which I think is a frequency of about, say, 100 or 200 hertz. So that's the minimum required response time to correct for the atmosphere. But in order to be safe, I think in general, AO systems operate about 10 times faster than that. So that kind of gives you a sense for how quickly all of this has to be done temporally.
Yeah, it just seems like at the end of that nano satellite's journey, 5 milliseconds could be quite a distance. Well,
so the farther away the nanocraft is, the longer it takes the light to return back to Earth. But it's only the last couple milliseconds that matter, because those last couple milliseconds are when the light interacts with Earth's atmosphere. So that time frequency shouldn't change over the course of the launch.
Oh, okay. Gotcha.
Yeah.
Matt?
Yes.
It's me again.
Hi, Daewoo.
So did you consider how accurate it needs to be when it now finally begins to free fly because it will fly long. It's a long shot, and how accurately you need to aim. I mean, to get there because it's far away.
Yes, incredibly accurate. So I guess I have a slide here which isn't strictly related to your question, but it is actually gives you the numbers specifically. So this, what I have here is an angular subtense of the nanocraft relative to Earth. And I have this angular subtense up so I could determine what the minimum telescope size would be to take an image of the exoplanet. And it has to be incredibly large. I think it's pretty much impossible. But I guess this angle here tells you what the pointing accuracy of the nanocraft would have to be if you wanted to impact the planet, which we're not trying to do. So assuming the solar system, as long as you're within the solar system, you can take high resolution images of Proxima and say the solar system's diameter was a 1 light year, you could determine what this angular subtense would be for a right angle here of 1 light year, and then the distance of 40 trillion kilometers to determine what the angular pointing accuracy has to be for the nanocraft at the end of launch, which is, even with this increasing from about the radius of the Earth to 1 light year, is going to be an incredibly small angle in the sky. And you also have to not point where Proxima is relative to the sky now, but where it'll be in the sky 20 years from now, which is kind of an interesting thing that when you have to consider the motion of the stars over the course of 20 years for this system. It's also interesting because if the sail is oscillating back and forth, and say you figure out a way to dampen that oscillation, when the beam turns off, it's not only going to have the motion towards Proxima, but it's going to have whatever lateral velocity it had right at that last moment. So there's probably going to be some statistical probability at which the lateral motion right at the last moment is 0, and it's only moving towards Proxima. All of these things, which seem like low probabilities, are being mitigated by the fact that Starshot is sending hundreds of these spacecraft with the assumption that 90% of them aren't going to work. But as long as one of them does, then we call that a mission success.
Thank you.
Do we have other questions from the audience?
I've got a question.
Yeah, Jaren.
Yeah, I guess back to the donut PSF. I really like the name, first of all, but I was wondering if it proposes to generate I guess a solar sail sized donut PSF.
Why, one could almost say I planted you in the audience to ask this question. I didn't, by the way, but I have slides prepared for that exact question. So, so an error PSF, that's the focus distribution of an aperture with a uniform illumination of equal phase across that aperture. And you can generate a PSF mathematically by Fourier transforming that circle, uniform illumination, uniform phase to the focal plane. You get an Airy pattern. There's 2 ways you can create a donut. The first one is by defocusing that beam by by plus or minus 1 wave. That's shown here on the left. The other way is, instead of having an aperture whose phase is uniform across the aperture, you vary it from 0 to pi azimuthally. So as you go around the aperture, you vary it from 0 to 2 pi. So it's like a vortex or a spiral phase. If you Fourier transform that to the focal plane, what you get is a spiral phase donut PSF. So they each have their own kind of aspects, but it's probably going to be the case that the Starshot uses the spiral phase donut PSF generation method. And that's to do with the fact that the encircled energy of the spiral phase is much tighter than the defocus. And that's important because the expected launch is going to be 100 billion watts, and it's going to cost about a penny per watt. So although it's only a penny per watt, 100 billion, that's a lot of money. So you want to increase the transfer efficiency of laser light from the projector up to the solar sail. And you can do that with a spiral phase donut, PSF.
Cool. Is the idea that you're putting these like spiral phase masks on a bunch of lasers on the ground that are then co-phased onto?
That's exactly right. So the launch projector itself is made up of millions of subapertures, and each of those subapertures is about the size of R0, which is a patch of the atmosphere, which all you need to do is control local tip and tilt across the aperture. So if you can, in each one of these apertures, change the piston, and you do that azimuthally, you can, across your launch aperture, change the phase to be whatever you want, essentially. And in this case, it would be a spiral phase.
Awesome, thank you.
You're welcome. Great question. Any other questions?
I have a follow-up, if I can ask another one.
Sure, please.
A lot of the analysis is contingent on describing the distributions of the perturbations on a normal distribution. I was wondering if you could speak onto how you know that it does indeed conform to a normal distribution of...
Yeah, so that just comes down to the central limit theorem. I don't speak very good statistics language, but if you have a random process which follows any distribution, and you sample that random process a certain number of times, and you take the mean of that sample, and you do that a bunch of times, the sample mean distribution, no matter what the random process's distribution is, will always be, most of the time, with some small exceptions, will be a normal distribution. So that's called the central limit theorem, and that's as deep as I want to say without misspeaking.
Gotcha. Thank you for the clarification.
Yes, you're very welcome. It's very cool. I highly suggest, if you're interested in learning some cool statistics, this is kind of a fundamental one that's very powerful, and as you can see, very useful when analyzing complex problems that you don't know the distribution of a certain thing. Its sample mean is probably going to be a normal distribution.
I have one more question.
Sure.
We talked a lot about the uncertainty in lateral position of the nanocraft, but what about the position along the optical axis?
Yes, that's a great question. So in my analysis, I always assumed that it was always perfectly at focus. However, you can expect that in this moment here, say, for example, it has a component which brings it back to the center of the optical axis, but it's also seeing more irradiance and more irradiance along the optical axis. So in this scenario, not only is it going to be brought towards the center, but it's also going to be pushed forward faster. It's going to feel more force. Which essentially means the shape of the distribution change, the shape of the donut changes, because you're no longer at focus, you're ahead or below focus. The hope here is that if you start to lead the focus, the distribution, the donut will broaden and the peaks will reduce, which means the acceleration velocity will, the forward force of the sail felt by that defocused donut is going to be lower. So then it's going to start to lag back down towards focus. And that can actually happen. So there's not only is there an oscillation left and right, but there's probably going to be an oscillation forward and backwards, which I didn't analyze, but that could be an interesting thing to do for future work to see how that affects the flight stability given a certain amount of required dampening, oscillation dampening.
Thank you.
Okay, I think at this point we will want to move into closed session with the candidate.
Okay.
So Matt, thank you very much for
Yes.
a very interesting presentation.
Thank you.
If I could ask you to stay and the committee to remain, and we will excuse everybody else.
Yes. Thank you, everyone, for coming. I really appreciate your support and being here. I'll probably be in Opti after this, so you'll hear the results then. So adios to everyone.
Okay, it looks like it's just you and us.
Yes. Hello.
Well, I mean, I have just a couple of very minor comments. You had my feedback on the written.
I did.
document. Hopefully that made sense.
Yeah, I did. I appreciate those comments.
Yeah, but maybe we should let I should let the other members of the committee ask questions.
So, well done. And I asked my questions, I mean, during your talk. I have one more question. So everything is trade-off in life. So let's say your spherical sail versus flat sail. Spherical sail brings you the passive auto adjusting.
Yeah.
What do you lose compared to flat sail?
Yeah.
Can you that?
Yeah. So with a spherical sail, you get stability, but you also lose a lot of acceleration force because the magnitude of radiation pressure is both the combination of the intensity of the light and its angle of incidence. If you have a spherical sail, and all the rays that hit that spherical sail on its sides will come in at a grazing incidence and reflect at a grazing angle. And because that angle of incidence is large, the magnitude of force felt by the sail from those rays is much lower. So essentially the energy transfer efficiency for a spherical sail is much lower than a flat sail. Flat sail, all of the beams, all of the rays come in and they reflect at a normal incidence, imparting the maximum amount of momentum that they can, accelerating it much faster. So that's the trade-off that's what you lose with a spherical sail.
Thank you.
Yeah, the more you think about this problem, as we've been doing, Matt and I and the rest of the team for the last year or so now, the more you realize it's really hard.
Yeah, and it's always harder than you can ever fathom.
Right.
You start to think about one problem and then you discover something even bigger that you hadn't thought of before.
Matt, however, I have a little bit different angle on this project. To me, you don't have to fly that far, actually. If you can fly or anything like that with this, I think that's beautiful already.
Yeah, I actually did a small little back of the envelope calculation on what a small scale Starshot system would look like. A small scale, like getting to Saturn within a week. And what that would look like and if that would be possible. And essentially what I found was if you look at the current trajectory of telescope sizes and you extrapolate that 50 years into the future with 3 fairly large nuclear power plants over the ridge and the largest projected telescope size, you could probably do, I think I found 1% or 1/10 of 1% of the speed of light, which is incredibly fast and gets you to Saturn, I think, within a week. So that's pretty cool that actually could be potentially possible if you could figure out a way to make the beam stable, the flight stable, and have a material which can withstand that amount of force.
Right. So interstellar mission is cool, but interplanetary is still, I think, pretty exciting.
It is. I agree.
I didn't mention about this in your, because your writing was good, by the way.
Thank you.
In my opinion, it was good. Or well done. I wonder if you considered, I mean, the variation of the reflectance in your sail. So it's not the, let's say, spherical sail, but let's say your reflectance is varying as a function of position on the flat sail. So if your donut beam shines, I mean, one side, it may give you more energy in one direction, maybe. But in that case, you are not really, so did you consider such a thing also?
I did not. In my simulations only considered a spherical sail within a donut PSF where the sail has is perfectly reflective. Yeah, okay. perfect reflective. But I know that a concept had been considered where you could still use a flat sail, but you could use it, the material would be diffractive, and the diffractive properties would vary radially, such a way that with a Gaussian profile and a flat sail, it would still give you that passive restoring force. What was the name of the gentleman who came up with that concept, Michael?
Oh yeah, he's our vortex coronagraph guy, whose name I can never remember. At Rochester, used to be at the college, right?
Yeah.
On the tip of my tongue.
Yeah.
Oh, the vortex at RIT.
Yes.
The Rochester Institute of Technology. Oh.
Yeah, I can't either.
Exactly.
Yep.
Yeah, that guy.
Yes, him.
I got some questions. I think is now a good time. I'm sorry I was late joining you. Let's see. I think it's very nice, Matt, and I think it's great if you can find the silver bullet into the heart of this thing, right? Because we come so close to it in various directions. And it sounds like you may be close to one. I wanted to understand. It sounded as though your statistics of tilt error are 3 nanometers across the 4 kilometers on a time scale of a 30th of a second. Is that right? That's what was driving your
Yes, that's
play.
correct.
And how did that come up with? How did you decide on that as the amplitude and time scale of after AO correction?
Yeah, so I had initially started with 15 millimeters as the standard deviation for beam decenter as a starting point that I thought would be small enough that that it would not even be an issue. And my plan was to slowly increase that standard deviation from 15 millimeters up to whatever limit would cause the sail to be unstable. And what I found was that at 15 millimeters, that was too much. So that's how I decided where to start. And then with regards to the frequency at which these oscillations, these perturbing forces occur, I figured that using the Tyler frequency of the atmosphere would be a good metric for determining how often these forces occur, because you're correcting this tip and tilt at the frequency that they are occurring, which is the Tyler frequency. Does that make sense? Did that answer your question?
Is the Tyler frequency R0 over the average speed or something like that? I'm not familiar with Tyler.
The Tyler frequency is essentially, it's about 1/9 the Greenwood frequency.
I'm sorry, I only remember R0 and the speed of the turbulence. So,
okay, so the speed,
how does it connect to that?
Yeah, so the speed of the turbulence is related to a value tau naught, which is how fast the aberration changes from moment to moment, how quickly you essentially have to run your system at. And so the Greenwood frequency is 1 over that time scale. And that tells you the frequency at which aberrations change. And the Tyler frequency is much slower than that. So if you look at how fast wedges in the atmosphere present themselves to the adaptive optic system, they present themselves much slower than higher order aberrations, and the ratio between those two is a factor of 1/9.
Well, compared to normal AO, there's an outer scale of turbulence, right, which may be 10 or 20 meters, and we are many, many times that. So I would think that you would have to, from the sort of fundamentals of this turbulence moving across 4 kilometers, you know, in a small period of time, a little bit of turbulence goes off one end, a bit new comes in the other end.
Yeah.
Plus, you've got a bunch of errors that you're making because your correction is not perfect.
Yeah.
I think it would be good to think specifically to make sure that when you're talking about correcting 4 kilometers, that your model of the atmosphere and your correcting process actually is consistent, because this number is critical, and it's the question that your work, which is very interesting, right, really throws up what is really the change in tilt and what is the frequency of it. And I would think modeling something on this on this very big scale with some model of the atmosphere, and that this may be what the PhD follow-up is. I'm not suggesting you need to do this for the masters, but I just happen to have been writing on building a 20-meter telescope on the moon, and you can obviously get around all this by going to the moon. But there is a halfway point, which I've also written about in the past, which is the South Pole, or at least Dome C.
Mm-hmm.
Because the turbulence there is very different from, say, in Chile, where you might have been thinking of doing this. It only apparently extends 100 meters up in the atmosphere. And the speed of the air motion there is probably much slower than what you would have. You can get to these points, you know, around Antarctica, you have huge winds, but as you get into the bulk of the continent, like at Dome C, then you get quite slow winds and very low turbulence. So that would be another thing that if this really turns out to be the killer silver bullet here, going to the moon is going to not be a solution because it's going to be too expensive, I think.
Yeah.
But Antarctica and Dome C might just be credibly a place to do things. So it would be interesting that if you have an atmospheric model going and an AO model, putting some numbers that get to what this critical number is would be a very good thing to do.
Yeah, I agree, because the accumulation of oscillation energy over time is a function of the magnitude of those perturbances and their frequencies. And in my analysis, right, I kept the frequency of the perturbance fixed, and I didn't perform any analysis on how changing that frequency affects this flight stability. My intuition is that it's, of course, if you reduce the frequency of perturbing forces, the accumulation of energy is going to decrease. So that would be an interesting analysis.
You have feedback here on the tolerance with which you must control phase of the lasers across the 4 kilometers, right? Because in at least the thinking that I was doing with this, you were thinking of getting 80% strail or something. You would think you were doing incredibly well across 4 kilometers. But now you're saying, nah, we want 3 nanometers across 4 kilometers, which is a whole lot better than 80% strail.
Yeah.
And, you know, the usual methods of adaptive optics, like Shack-Hartman wave front sensing and integrate. Well, for starters, you don't have any continuous surface to integrate over, right? So you can't just integrate slopes. And even if you could, by the time you've integrated them across 4 kilometers, you're toast. So it means that the sensing of phase from a phase reference beacon becomes, I think, absolutely essential. You can do local stuff from slope integration, but for the whole thing. So now you're saying that those phases from whatever reference you're using, something on the mothercraft or whatever, those are going to have to be measured to 3 nanometers, or at least in some way that statistically averages out so that that's the size of the error.
Yeah.
So assuming that there's no way out of this, you said that maybe damping is possible. Has anybody written anything about how anything could apply damping?
Not that I could find or have read, especially with regards to Starshot.
We had one idea from Ryan Luder a while.
Oh yeah, yeah, that was an interesting idea actually. Which you want to explain, Michael?
Oh well, so Ryan's thought was you charge the sphere. So as you accelerate the charged sphere, it will radiate, and it will radiate in such a way as to damp out any lateral motion. But when you work out what voltage you have to charge this thing to,
it's
really good. It was something on the order of 10 to the 18 volts, which is probably a bit impractical. But at least the physical principle was good.
Right. Well, you'll make a huge lot of enemies if you actually are able to kill this thing.
Yeah.
You'll prove yourself one better than Stephen Hawking, right? But at least you've started a path down that line.
Yes.
Let's see. So one thing, one very minor thing, Matt, caught my eye. You will hate yourself if you don't fix this. There's a couple of pictures in there which talk about perfect reflection.
Yeah.
They are labeled prefect reflector.
Okay. Okay. Thank
yeah.
you for spotting those.
Right. You've put so much effort into this. That's evident.
Yeah.
One thing I would just caution, a couple of times you talked about A being proportional to B.
Mm-hmm.
For instance, I think you said that the focal anisoplanatic, or maybe the angular anisoplanatic error was proportional to the angular offset alpha. You might want to be a bit careful about that. It's not proportional to, it is dependent on.
Okay.
But it is, you know, when somebody says proportional to, they generally mean a linear relationship.
Okay, got it.
And it ain't, and that came up.
Got it.
Anyway, that's just.
Did I do that in my paper, or were you just referring to my presentation?
I don't remember seeing it in the.
Yeah, I don't think I had it in my paper, but yeah. Okay, that makes sense.
But that was about the extent of my additional comments beyond what you saw there in my written feedback.
Awesome.
Pretty minor stuff. No, I think this has been a most excellent piece of work.
Thank you, Michael.
If you wanted to stick around, it wouldn't have taken much more to push it to the PhD level.
I appreciate you saying that.
Let's see, we're at an hour and a half. Are there any other questions or feedback, comments?
Yeah, I'm done.
Yeah, I just want to say this was one of the most impressive master's defense this year, actually. So,
thank you.
Well done. I mean, the thesis looked good, but presentation was also very well organized and planned. So, thank you.
Thank you, Daewoo, very much for saying that.
Okay, so at this point, I guess I have to learn how to set up a private chat room.
Yeah, I know how to do it, so I can set that up and send you guys off if you'd like, Michael.
Michael, you may just send a Matt to the waiting room, because you are the,
yeah, that works too. That works too.
You are the co-host. You can just send him to a waiting room.
I can send him to his bedroom without his supper.
You have almighty power.
How do I do that?
Maybe go to his name, I guess, and then right click or something like that. There must be a...
Yes. The little 3 dots on my picture, if you click on that, there's a button that says put in waiting room.
Mute audio, stop audio, chat, pin video, spotlight video. I don't see a...
Oh, it's only possible if you are the co-host. Matt, did you give Michael co-host authority?
I did. I'll make... Yeah, you are co-host, so or maybe
While you do that, I'm getting coffee.
Okay.
I can remove a participant, but that seems a bit drastic.
Let's see. Maybe Michael, I'll give you the host.
Okay.
I'll give you the host, and you can.
Yes, give him the host because you may not leave if you are a host.
Yeah.
So,
okay. So let me do that.
Okay. You are the host now. All right.
So now I'll give that another go, kicking me out.
Now I have more options on your 3 dots. Yes.
Okay.
Okay. Let me put you in the waiting room then.
Okay.
For a few minutes.
I will await my return.
Right.
and you may want to stop video recording now.
Oh yes, let me do that real quick.